So let's talk about the advantages of experiments over observational studies. And we talked a little bit about this. Well, first of all, in experiments, oops, let me go back. Lord. Experiments allow us to study the effects of specific treatments we're interested in. They allow us to get the combined effects of several factors simultaneously. And basically, experiments can give us good evidence for causation. And a lot of times when we're doing an experiment, we'll actually use something we call a placebo. And a placebo is like a dummy pill, and it looks and tastes like the real thing. And so this is kind of funny. Nurse, bring this man a placebo stat. So obviously, it's a dummy pill, so it has no effect on the person or thing that it's the subject, I guess. And so that's a good way to control an experiment, to test whether or not there is a factor. So we're going to talk today about the principles of experimental design. And so first, you need to have a comparison, a design that compares two or more treatments. And again, this is one of those places where a placebo comes into effect, because you can have one group that takes the placebo and then one group that actually takes the pill or whatever the treatment is, and you can compare that way. Random assignment. So we know randomization is extremely important when we're doing an experiment or a statistical survey. And so you want to use chance to assign experimental units to treatments. And this helps roughly create equivalent groups, balancing the effects of other variables among the treatment groups. So you get relatively the same people in both kinds of groups, no bias. You want your control. You want to keep other variables that might affect the response the same for all groups. So it can be, like I said, it could be using a placebo. It could be using the same environment. There's a lot of things that we're going to talk about that influence your control. And then you want to use enough experimental units, enough subjects in each group so that any difference in the effects of the treatments can be distinguished from chance. So you want to replicate the experiment several times. And if you're going into the science industry, this is something that they do a lot, especially if you want to be in pharmaceutical science. They use a lot of replication to test, say, dosage of pills. I was talking to my brother this weekend, and he said they use statistics all the time. So say you have a headache and you want to know, you take a pill for it. They've actually done so many replications of an experiment on so many different subjects that they can predict how long the drug takes to run its course in your system. And so that's how they know how much of a dosage you should take, which is kind of interesting. Okay, so control again, it refers to the overall effort to minimize variability. So you have your experimental units, you give them their treatment, and then you measure the response. And you want as much control in this simple dynamic as possible. So a lot of times these are done in a laboratory environment, and these simple designs really work well there. But if you're going to do a field experiment or experiments with animals or people, there's going to be a lot more variables that are going to play in. So outside the lab, you don't want a simple, badly designed experiment. Otherwise, your results and all your time is wasted because of confounding variables, which are those other things that impact your results that you don't want. You want to control those away. So what can go wrong? Well, there's a thing called the placebo effect. And actually, some people, even though they're taking a placebo, respond positively to a treatment. And your control group is the group that receives the sham treatment, right? So they're the people that your control group is going to be the people that receive that placebo. And it is the major basic principle of statistical design experiments. You want to make sure that you're comparing several treatments in the same environment, and that is your simplest form of control. Replication, we talked about. It is to make sure that you're using enough subjects. You want to make sure you have a controlled environment, that you're using enough subjects so that you can reduce your chance of variation. Randomization. Some people say this is the most important principle. But basically, you want to make sure that your treatment groups are essentially similar and that there's no difference between them before the treatments are administered. Otherwise, again, this could cause a skewed result. And then last, you want comparison, but comparison isn't enough on its own. If the treatments are given to groups that differ greatly, bias will result. So that's why randomization is so important. So let's look at the outline of a randomized design. So in a completely randomized design, the treatments are assigned to all the experimental units completely by chance. And this is where you use either your calculator and you hit math, scroll over to PRB, hit number 5, and you get a rand interval. And that's where you're going to type in your subjects and you're going to give them all a number from however many subjects you're going to select. And that's how you put them in there, either the control group, and that's the one that's going to receive the inactive treatment or the placebo, or they get to be in the subjects where they're going to actually get the treatments. And so what we do when we design our experiment is we first start with an outline. So the first thing we always want to do, just like when taking a survey, you define your population. You're going to define your experimental units. And remember, people, animals, plants, things, whatever it is. Then you're going to do your random assignment to determine who's going to go into group 1 and who's going to go into group 2. And again, your random assignment comes from a random table or from your calculator. And then you're going to define the treatment. So treatment 1 might be the control treatment where they get the placebo, and treatment 2, let's just use aspirin as an example, they're getting a dosage of aspirin. And then you compare the results. And the results might be, did you still feel a headache after taking the pill? All right, so here's our first example. I will do this one with you, and then the rest you will have to do on your own, and I will give you feedback when you turn your notes page in. Again, it's for a grade. Does talking on a hands-free cell phone distract drivers is our statistical question. And so what we did was we had undergraduate students, that would be our experimental units, also called subjects. Our undergraduate students drove in a high-fidelity driving simulator equipped with hands-free cell phone. The car had brakes, and we want to know how quickly does the subject respond. So our experimental units are undergraduate students. We randomly assigned 20 of them to be in group 1, which is our control group, and then we assigned 20 of them to be in group 2, which was our experimental group. Then in group 1, the treatment was that they just drove, so there was no distractions. In treatment 2, we had them talking on their cell phones while they were driving. The car had brakes, and the results are how long did it take you to respond to the car ahead of you braking. So how long did it take you to brake, essentially, was our results. And so that's simply what an experimental outline looks like. So now you're going to try a couple on your own. And some of these you actually do have to do the random assignment, and I will explain how to do that when we get there. So example 2 is multitasking. You'll see space to fill in your answers for this on your note sheet. Researchers in Canada performed an experiment with university students to examine the effects of in-class laptop use on student learning. So all participants in the study were asked to attend a university-style lecture and take notes with their laptops. Half of the participants were assigned to complete their non-lecture related online tasks during the lecture. So they were listening and taking notes, plus they had to do some other things on their computers as well. These tasks were meant to imitate web browsing during class. The remaining students simply took notes on their laptops. To assign the treatments, the researchers printed 40 papers with instructions, 20 with the multitasking instructions and 20 without, shuffled them up and handed them out at random to students in the classroom. At the end of the lecture, all participants took a comprehension test to measure how they learned from it. Okay, and so if we're looking at our outline here, you want to go ahead and fill in the outline with who were your subjects, who was in group 1, who was in group 2, how were they randomly assigned, and so on and so forth. Pause the video and finish that, or continue working and do it later. So let's recap the principles of experimental design. First, we've got comparison, and so that's going to be comparing 2 or more treatments. You've got your random assignment, and that uses chance to assign experimental units to treatments. Control is when you keep other variables that might affect the response the same for all groups. And replication is that you're using enough people or enough subjects or enough experimental units so that any differences in the effects are explained, I guess. And so we hope to see a difference in the responses so large that is unlikely to happen just because of chance variation. And when we have that, we have something called statistically significant. It's an observed effect so large that it would rarely occur by chance. Okay, here are some more examples that you are going to work on your own. So you're going to need to read the experiment, pause the computer, read the experiment. The first thing you're going to do is make an outline for the design, and this is kind of the framework we've been using. And then down here you have a list of 20 subjects, and you're going to use your graphing calculator or that random table, line 131, to randomize your design. Please remember that the first thing you need to do is in alphabetical order. You need to assign each one of these subjects a number between 1 and 20. And then you go in your calculator and you're going to hit math, PRB, 5, and then you put in the parentheses 1, 20. It'll be rand interval 1, 20, and you keep hitting enter until you've selected all 20 of your subjects to go in whichever control group you want them in, or whichever experiment group you want them in. Here's experiment number 4. Again, you're going to need to pause the video, read the experiment, draw your outline of how the experiment looks, and you can either go to line 142 in the random table to assign your rats to treatment, or you can use your calculator. Again, it's math, PRB, 5, and that'll give you rand interval. And then in this case, however many rats you need to assign. I think it's 18 rats. So it'll be 1 to 18. So in experiments, what actually can go wrong? And so the first thing is that response to a dummy treatment is actually called the placebo effect. So if you take a placebo pill and you actually have a positive response to it, that's called the placebo effect. And we also have a double-blind experiment, and that is where neither the subjects nor those who interact with them, let me hold on for a second.